Alright, so today I'll cover the lecture slides for Lab 2, which is a lab on doing discrete event system simulation by hand. And we are going to use this muffin-baking operation as the system that we're going to model using a DES simulation model. Alright, so just a recap of what we've got so far. So in these DES models, we refer to entities and attributes. The entities are the things kind of moving through the system passively. Each one of them has attributes that differentiate themselves. So an entity could be, people, and attributes could be different aspects of those people, whether, their age, for example, things like that, or what time they entered the system. That could be an attribute as well. Those entities have to wait on resources to become available. So those entities would like to have a certain activity. So that's these activities here. Those activities take time, they're durations of time, but in order for an activity to be completed, a resource has to be available. And when resources aren't available, those entities have to wait. And so they're delayed while they're waiting for an activity to start. So an activity is something you're doing with a resource, and a resource is has a limited capacity that has to be waited on in order for entities to receive service. And then we have states, and so states, the state of these are dynamical system models, and so they're constantly changing as they go through time. And so at one time the system is at a particular state, and at another time the state might change. So the state might be the number of people waiting. It might be the number of resources available for service. So those are the current state of the system, is what we refer to as the state. And then if we create a mathematical quantity that sort of keeps track of that, allows us to do bookkeeping in our simulation models, refer to those as state variables. So, a variable is like X, Y, or Z, and then, X can equal a bunch of things. So X equals 2, that tells me that the state variable X, it represents a particular aspect of the state. If X is equal to 2, then right now 2, that's the state the system is in, and the state variable is X, and so that's the difference between those two. Now an event, those are the instance of time to differentiate from activities where the state changes. So if the state was 2 and then it jumped to 3, the instant that it jumped to 3, that represents an event happened. So events represent when states change, or the other way to look at it is when states change, we record an event. So we're interested when states change. So that gives us the so-called event calendar in a discrete event system simulation model. And so it represents these irregular jumps, and so we don't really care about the system between events, because that means that the state has been the same between those events. We only care about the system when it changes. And so in a computer simulation, that means that actually can make these types of simulations relatively fast, because we can just jump to the next time where the state changed, rather than simulating a bunch of time in between state changes where nothing is changing. So there are other simulation methodologies that actually just simulate time on a clock, so that regardless of what's happened in the system, they always simulate one more second or one more millisecond of time. And that's in those types of simulation frameworks, you actually don't know when the next event occurs. But these discrete event system simulation models are formulated in such a way where we always know where the next state change will be, and that allows the computer to jump from one state change to the next and skip everything in between, which can make them faster. But the consequence of that is they get irregular jumps. And so notice that some of these jumps from event 1 to event 2 might be small, but other one of these jumps, like this one from event 3 to events 4, 5, and 6, well, all those events might have happened right at once, might be very long. So we get these, if you watch a discrete event system simulation run, then sometimes it can seem kind of strange because you don't get necessarily smooth movement. You might go from seeing 1 second, 2 second, 3 second, and then suddenly 1 hour, because it just happened to be that you had no events generated after second 3 up to the first hour, and so you just jump across all of that. All right. once you're done with these simulations, then just like you would in a real system, you take performance measures. And those performance measures allow us to compare one simulation setup to another. So as an example, these are some common ones you see in, say, manufacturing type problems. So total production of parts over a run. So a run might be one simulation run, and we're just simulating, we run the run until the day is over or until we're out of parts or something like that. And we can then count, well, how much production did we get during that run? So if we rerun it, we might get a totally different number because of the stochasticity in these systems. And then we can then sort of figure out that, well, with a certain schedule or for certain scheduling or certain, things that we can change in the manufacturing system, we tend to get more parts produced under one situation than another. We could also measure, per part, what is the average waiting time for this part or this customer to get serviced? What is the maximum waiting time for this part or this customer when they're waiting for service? Then we've got these time average, so the number of parts in the queue. Well, we can say, well, if we, at every instant of time, we can count how many parts are currently waiting for service. And if we then sort of take the integral underneath that and then divide it by the total time of the simulation, that gives us a so-called time average. So instead of an arithmetic mean, it's sort of the integral version of an arithmetic mean, where instead of dividing by a count of things in the mean, we're dividing by a length of time. Maximum number of parts in the queue, that's another way we could look at it. We could say at any instant of time, how many parts were waiting for service, and then we can always ask, then over all of the time, what was the maximum value that hit? And then things like average and maximum total time in the system, these hopefully are kind of self-explanatory, and then things like utilization. And I'll give examples of utilization that you'll measure during this lab to make that more clear if you're not already familiar with this sort of idea of utilization. But the basic feature of utilization here that we're trying to measure is how much of the provided resources are we using. So we might have provided 4 clerks in a particular setup dealing with customers, but not all 4 clerks are used. And so maybe only 2 are used most of the time. So in that case, we maybe have a 50% utilization. So how much sort of idle time do we have in these clerks? So total, maximum, and average, you see those show up a lot here. These are good indicators that we are using a performance measure. So sometimes students have trouble differentiating between state variables and performance measures. Keep in mind that state variables sort of give us an instant snapshot of what's going on right now, whereas performance measures are kind of taken across the entire simulation. So over all time that we've simulated, and then they aggregate all of that into sort of how well did we do during this simulation run. So they aren't a state variable, although we might keep track of them as we're simulating in a similar sort of way, but they are kind of aggregating across the history of the simulation as opposed to just keeping a snapshot of what's going on at one particular instant in the simulation. All right, so today, what are we trying to add to that? Well, so as we're moving forward here, now that we know what events are, we need to be thinking about what goes on in a simulation at each event. So at each event, the state of the system changes, and so we need to sort of figure out, okay, well, so certain events, how do they change the state of the system, and how do they change the future execution of the rest of the system? So that's what we're kind of seeing here today, is identifying what happens in a simulation whenever you jump from one event to another. So before you can get set up to jump to the next event, you have to change the state of the system. So in our computer models, this will be done automatically for us. We'll provide some guidance for the computer on what it should do, but then it will do all of the kind of, tiny steps. In this lab and in one of your first homeworks for this class, you will be manually doing that just to sort of better appreciate what's going on behind the scenes. So the other thing that we're going to be working with here is to sort of give you a basic idea through this hand simulation process of how in simulation we can do things like compare systems with different either scenarios or different scheduling policies and so on. So we will focus here on these event triggers. So in other words, we're going to say, well, what if I've got this system that I have to wait for a certain number of entities to show up before I can start service? Well, do I start service immediately, or do I have to wait for all of me to sort of fill up my all of my available service capacity before I go into service? And can I compare the performance of each? So we'll see that. And in doing so, we also then will get exposure to resources that have more than one capacity. And so in a lot of the examples we'll see early in the lectures, we'll start with resources that only have a capacity of one. So there's only one server. So in this lab, we start to see how you can have a single resource that has a capacity that is larger than one. So it can handle more than one entity at a time. And although we won't really get into it here, this sort of gives you an idea moving forward of how we can think about servers that are used in special ways. So for example, you can cross-train servers so that a server can be used on multiple different types of entities based on whether it's needed for it to work on those different types of entities. And so we talk about cross-training in the case of human operations, and so you might train somebody can only do, handle ringing someone up at a cash register, whereas someone else can not only do that, but they can also make someone's coffee. And so based on how busy things are, then people will then move from one job to another within what they're trained to do. But sometimes they're not trained to do that much, and so they are stuck doing one job, even if that means another job is very, very busy, because they just can't help with that. And so hopefully you can see with these sort of conditional triggers that we're going to do with these different batch types here, how you can maybe get into seeing how cross-training might work. But in general, the big thing I'm hoping you'll see is, beyond just how we manage the events and the event calendar, how you compare systems of different types. All right, so the basic setup for the lab here, it's another 30-point lab, but I'll give you 2 potential bonus points in this lab. It's an individual mode lab, so all your submissions should be unique, although we'll see that the uniqueness of the quantitative part is going to be limited because depending on the last digit of your ASU ID, you may be, be dealing with the same data set some of your other students will be dealing with. But so of course, if you both answer correctly, you're going to have very similar quantitative solutions. But I'm hoping in the qualitative answers to the questions, those solutions should definitely be unique and reflect your own individual understanding. So we're going to do a discrete event system simulation by hand and identify the steps needed in order to execute these DES models that will eventually be done inside the computer, but we need to make sure you appreciate that before we hand it off to the computer. What you'll submit is a Microsoft Word document with a couple of report questions, which will be at the end of these slides, and then also an Excel spreadsheet that has the quantitative solution to these by-hand simulations. And this will be due on Sunday night. All right, so let's get a little background. So imagine so this is the system that we're modeling. We're modeling the baking of muffins. And so muffins arrive to an oven, and this oven has a certain amount of capacity. So in the picture that we see here, we've got 12 muffins that can be baked here. Now, what if whoever's making the muffins happens to bring us 10 and gets a little backlogged and can't end up making us the other 2 to put in the muffin in the oven? Do we wait for those other 2, or do we just let the muffin go with 2 empty spots right in here? And if we let it go with those 2 empty spots, the muffin oven will be consumed for that, it'll be held over for that entire amount of baking time. And so once those 2 muffins are ready, they're going to have to wait. So it's not obvious whether we leave the muffin open and cool, the muffin oven open and cool, and wait for those 2, or we just bake these 10. And so depending upon the arrival rate of muffins and all of those sorts of things, then you might find one policy is better than another, and then that might switch in other scenarios. And that's kind of what we're exploring. So in here we're going to assume a deterministic arrival schedule of muffins. So what we mean by that is that every minute we get one batch of muffins. So the first batch arrives at time 0, and then we have to decide whether we put this batch in the oven or we wait for the next batch. Now, the stochasticity is introduced because the size of these batches changes. So we might have 2 muffins in a batch, or we might have 12 muffins in a batch. So I'm saying that the batch number is stochastic. We'll provide you in this lab what the numbers are per batch, but you can think of them as being generated randomly, drawn from a random distribution. But we just haven't gone into how we draw them randomly from a random distribution. So I'll provide those to you. But imagine if every time you go to the next batch, you ask a random number generator how many muffins are in this batch, and that's basically what you have here. So this is the only source of randomness in the simulation. So in a lot of our lecture examples, the randomness is in the arrival schedule. It's what's the distance between arrivals? How much time is it between the batches? But here we're saying a batch arrives every minute consistently, but the batches change in their size. So a lot of demand simulations, like the famous news vendor problem we'll talk about in class, this is much more the case, where you know that every day you're going to sell newspapers, but you have no idea how many newspapers you're going to sell. And so the demand is, the quantity of the demand is the randomness, not the time. And then service, muffins, when they go in the oven and they go into a baking cycle, bake for exactly 3 minutes. That's another deterministic quantity in this simulation. The oven can hold a maximum of 30 muffins. Once started, you can't open the oven up again and then insert new muffins. And so if you make the decision to start the muffin oven and then more muffins arrive, they have to wait for that oven to finish the 3 minutes, and then those muffins to clear before we can put any new muffins in that oven. So this is a dynamic model, and in all dynamic models you have an initial condition. So if you remember from your differential equations classes, you always had these initial value problems where you not only were provided a differential equation, but in order to solve it, you had to know the initial condition. It's the same thing here. We know how the muffin oven works. That's kind of like our differential equation, but then we also need to know the initial conditions. And in here, we're saying there's no muffins in the oven initially, so the oven's initially idle, and there's no muffins waiting in line initially. You can imagine starting the simulation in different states, where you start the simulation and the oven's already baking some muffins or something like that. In this case, everything's empty at the beginning. So the question is, how does the baking initiation policy, this schedule, affect the performance? So we can imagine kind of informing a hypothesis to answer this causal question. We can imagine these 2 experimental treatment groups. So a greedy batch policy. So that would mean that whenever the oven is idle, we start it immediately if there are any muffins in line. So if muffins arrive, it doesn't matter how idle the oven is going to be. If there's 2 muffins there, we just start them immediately. The alternative is we create a threshold of, say, 20 muffins, this nearly full batch, where we leave the oven open and accepting new muffins until we have at least 20 muffins waiting in line. And once there's at least 20 muffins waiting in line, we put as many of them as possible into the oven, we leave the rest in line, and then we start the oven. So the question is, what will be better for the schedule of arrivals that we've seen? And so you can imagine sort of making a hypothesis about, the greedy batch policy will be better. Well, if that's your hypothesis, then our prediction is that if we generate a bunch of muffin arrivals under different schedules, then we should see that the greedy batch policy maybe, generates a lower average waiting time per muffin than the nearly full batch policy. All right, so we're going to generate performance data for both cases so we can compare those two. All right, so how are we going to do that in the lab? So you're going to do this simulation by hand. There is a Lab 2 template Excel file attached to the Lab 2 assignment on Canvas. So I'm going to go over to that Excel spreadsheet here. When you open that file, as you see here, it's password protected. And that's as expected. This is to sort of force you not to accidentally, this is supposed to help you execute the instructions of this lab. So when this password protected prompt comes up when you open it, just click the read only button. And that should open it up here. I'll zoom in, and you should see some instructions on the first sheet. And you can see these instructions involve looking up your ASU ID number, going to the sheet that matches the rightmost number of your ID. So if this is your ASU ID, 6 is the last number. So you go to sheet 6, which is back here. And then on each sheet, you can see there are different number of muffins that arrive in each batch. So each batch arrives every minute. This is how many muffins arrive in that batch. And then our goal then by hand will be to fill out the rest of this table. And this is for the greedy policy, and down below it's for the nearly full policy here. And you should be able to calculate then these performance measures down here and then compare those performance measures. So that's going to be the instruction here. You download the template, you click on read only, then you follow the instructions, and those instructions basically are going to tell you to find the, I may have already closed that up. If I open that back up here, Lab 2 template, read only. If you right click on the sheet that you're supposed to open, you can see there's a move or copy, which you can click on, and then you can go to, say I want to create a copy, and instead under the to book, I can say new book. And if I do that, then it creates a new spreadsheet here, so I can close the old one that just has that sheet in it. And from here, I can save that as lab2.xls or xlsx, that's fine too. And now I'm ready to work on that one. And so I would only use this sheet if my ASU ID ends in 2. So modulate that based on your ASU ID, but you should be working on your own Lab 2 XLS, not on the template. So copy the sheets out of the template. And those instructions are on the template, and then I just kind of demonstrated it there. So follow it, create a new spreadsheet, save your working spreadsheet as Lab 2 XLS or XLSX, and that's what you'll end up uploading to your report. You're going to do the hand simulation, and then from the output, you're going to calculate, and this is also in that sheet already, the average time spent in the system per muffin, the average oven utilization, and the maximum number of muffins waiting for service in the queue. And I'll give some demonstrations on how to do that in the next couple slides. All right. So, how do we calculate the average time spent in the system per muffin? So, as you're generating your hand simulations, you want to keep 2 running counts. And so what I mean by that is for every batch, you update these counts. One of the counts you can call, I just called this one T_TIS, total time in system. You call it whatever you want, but you know that's one name for it. And this is the total accumulated muffin time, including both the waiting time and the time while in the oven. So the waiting time is a delay, the time in the oven is an activity. So every time you have an event where a single muffin leaves the oven, you add the time since its arrival, that includes both its waiting time and while in the oven, to the total time in the system. You also keep account of the total number of muffins that have left the oven. So every time a single muffin leaves the oven, you just add 1 to that count. Now you have to be careful because for both of these, usually the way things are set up, multiple muffins are going to leave the oven at the same time. And so if 3 muffins leave the oven, then you have to add 3 to the muffins that have left the oven, and you also have to account for the waiting time and activity time for all 3 muffins. And so you'll have to add 3 times to the total time system. So you add 3 to TNS and 3 to TTIS. And then once you have both of those, then at the end of your simulation, the average time spent in the system per muffin is just the TTIS, the total time in the system, divided by the total number of muffins, TNS. If you've already done homework B1, there are these other quantities, S and ND, and this works very, very similar to those. The other performance of the three that we have to worry about is the average oven utilization. Do something a little similar here. There's a state variable in S, which represents the number of muffins currently in the oven. It's a state variable because it's a snapshot of what is currently in the oven, current. We have another state variable representing the so-called instantaneous utilization of the oven. So that is how much of the oven is being utilized right now at this instant. That's why it's a state variable. So we calculate that by dividing the state variable in S by the maximum oven capacity. In our simulation, there can be 30 muffins in the oven at any time. So NS, which is always a number that is 30 or less, you do NS divided by 30, and that gives you the instantaneous utilization. Then we keep a running estimate, which I think in the sample spreadsheets is just called int B, but you could also call it integral B. That's what the int stands for here. But this is an estimate of the area underneath the instantaneous utilization curve. So you imagine this instantaneous utilization. It's a curve that, for one batch it's a certain amount. The next batch comes up, it might jump to a different amount. The next batch it jumps down to a different amount. And we can imagine calculating the area underneath that curve, taking the integral underneath it. Because every batch arrives I think I said it's actually every minute here, so I'll probably update that in the slides. It should say each 1 minute of the clock. Then we add B to int B, or integral B, each step of time. So each step of time is a minute, and so if we're adding the rectangle that we find in 1 minute to this area here, the width of the rectangle is 1 minute. The height of the rectangle is the current instantaneous utilization, and so that whole new rectangle is just 1 times B, and we're adding that new rectangle to the accumulated sum so far. So we're just adding B to int B every time. And then the average utilization will be that integral B divided by the clock at the end of the simulation. We end the simulation when the clock is equal to 30, so it's just going to be integral B divided by 30. The other performance variable you have to calculate is the max number of muffins queued waiting for service. So we have a state variable in queue, which represents the current number of muffins in the queue at any instant of time in the simulation. And we just keep a running count max in queue that has the largest value of in queue so far. So every time in queue changes, or just every time you have an event, you check to see the current value of in queue. If it's higher than the current value of max in queue, and if it is, update max in queue to be that higher value. Otherwise, leave max in queue at what it was. And that way, max in queue will always be the maximum length of the queue at the end of the simulation. All right, so if you're attending the laboratory, the goals for what you should do during one sitting is to complete a simulation by hand for either the greedy batch or the nearly full batch policy. So for your submitted laboratory report, you'll have to do both simulations and complete the report. But if you're just, a good way to make use of the help you can get from the TA is to just complete one of those and make sure you're comfortable completing that. Because once you can complete one, you probably can go ahead and complete the other as well. What we're expecting then in the report is an answer to a couple of questions here, actually a few questions here. So you'll create a Microsoft Word document that'll have an answer to these. So I'm asking you here that, ideally that we would like to infer which of these two policies usually results in a lower average time spent in the system per muffin. Now you've done 2 simulations, 1 simulation for each policy, and it is my claim that your work alone, your 1 simulation for the greedy policy and your 1 simulation for the nearly full policy are not enough for you to answer this question. And so what I'm asking you to report on is to tell me why. Why is the work that you've done in this simulation not enough to provide a good inference on which policy is best? What other work would you need to do in order to make a good inference about this? Now, with that in mind, you can go to the second question. Many of your classmates used muffin batch schedules that were different than yours because the last digit of their ASU ID was different than yours. explain how you could team up with your classmates to better understand the differences in the typical performance between the two policies. So your work alone isn't enough, but if you find others in the class and their work alone is also not enough, but I'm claiming that if you got together in a team with them, then how would your team actually provide a good answer to which one of these batches were better? So I'm not asking you to actually do this, but I'm asking you why your work alone isn't enough. But when you group together with others, then suddenly together as a whole, your team could finally answer the question, which schedule is better, the nearly full or the greedy? All right, so a little more advanced on this third question. I'm asking you to recall some of your statistics from previous classes, like IEE475. A two-sample t-test can be used to test the hypothesis that the means of the two populations, greedy and nearly full, are equal. So in other words, you have a bunch of greedy simulation runs, a bunch of nearly full simulation runs, and we, using these, might want to test to see are these the same or different? Is greedy much larger or much smaller than nearly full? Now, an alternative approach that has more so-called statistical power is the paired difference t-test. So this is another way to compare two groups. But you can't use a paired difference t-test all the time. This is also called a repeated measures t-test, and it requires stronger assumptions on the data. Now, it's my claim that the data generated in this lab, the way you've done it, if you followed the instructions for this lab, do meet the assumptions of the repeated measures t-test or the paired difference t-test. And I'm asking you to explain why. I'm asking you to tell me, why is it allowed, in fact, why is it almost pretty much required that you would have to use a paired difference t-test with these data? What did you do with these data that made them appropriate for the paired difference t-test? And then the bonus, going farther on than that, is if we didn't focus on the time in the system, if we instead focused on the maximum number of muffins waiting for service, why should we not use any t-test? In other words, there are certain assumptions of the t-test that get violated if you compare the maximum number of muffins between these two policies. And we need to find some other statistical test other than a t-test that allows us to compare these two performance measures. So what is it about this performance measure, maximum number of muffins, that makes it inappropriate to use a t-test? All right, so after you've done all of those, you'll have a Microsoft Word document, a doc or a docx file, that has your answers to these report questions. You should upload those, and that gives us the 6 points plus the 2 potential bonus. Make sure that you solve for all 3 performance measures in both simulations, and then once you've done that, then you also will upload the Microsoft Excel workbook, which is probably going to be called lab2.xls if you follow the instructions, or XLSX, that works fine too, with the completed simulation results for both the greedy batch and nearly full batch policies for the random muffin batch schedule corresponding to your ASU student ID number. And that will be 24 points. So added together, that's what gives us the 32 points, or the 30 points plus the 2 bonus. And that's it for this lab. So good luck, and if you have any questions, you can, again, if you've gone to the lab, you can ask the TA. Otherwise, you can send us an email or come to office hours.